This is, well, it's a rocket, but it's not a lot like the rockets we see ISRO, NASA, or SpaceX fly. It is a model rocket. Is it a toy? It's definitely not a toy. It's something even better. It's an educational tool. Does it serve any real purpose? Well, apart from the learning it provides while building it, no, but you gotta agree, isn't that the most real purpose something could ever fulfill? Meet Ananta, the first rocket that our team ever built. Now, over the past 2 years of the existence of the VGEC Rocketry Team, VRT for short, we've worked on a lot of projects and quite a handful of rockets, but we've never been very public about it. To be honest, video creation was a challenge that we weren't to tackle just yet, but here we are now, ready to talk about our projects. So, coming back to Ananta, it was the first rocket that we ever made and something that we were working on for more than a year. It took a while to perfect this. At its core, when Ananta was conceptualized, it had two primary goals. One, to be a model rocket, and two, to be so with as simple a design as possible. It had to be simple, so we decided that a rocket that could get to 200 meters and be recovered safely was a good target to achieve. Yeah, it really wasn't. In hindsight, going with a 50 or a 100-meter launch would have been a much better stepping stone. But hey, at least we got to make some lifelong bonds through shared pain and suffering, right? If I had to take a pick, I guess the hardest part of this project was the motor. We could not, and to an extent, still are not able to get the motor to perform reliably. There are several inherent flaws with the design. Let's go over them one by one. First of all, we chose to use a PVC pipe as the casing. At the time, we had two options to choose from: go with a metal casing, either steel or aluminum, or go with a PVC casing. These were the simplest and cheapest options available to us at the time, and we figured, hey, this is a pretty small rocket. A metal casing would be unnecessarily heavy. This was mostly right, but we severely underestimated how hard it would be to get the PVC casing to not melt or break or pop or just basically give us a really hard time. The foremost problem with the PVC was its melting temperature. For some reason, rocket engines get really hot on the inside. We don't know why, we're trying to figure that out, but it gets quite hot on the inside, and the PVC really does not like that temperature. As if that isn't enough, every time we tried blocking the heat of the gases from getting to the PVC, we just kept finding new ways to melt it. Eventually, we found that making the fuel inside of a paper tube called a liner, then inserting it into the PVC casing helped insulate the casing from the heat. In addition, we added a thin layer of an insulating compound made from baking soda and corn flour between the end cap and the fuel grain closest to the end cap to prevent failures where the gases would find their way through the gap between the liner and the end cap and melt the material just below the end cap. That's a lot of end caps. On a side note, if you're new to model rocketry and are having a tough time understanding the words I'm using like fuel grains and end caps, rest assured we will be making another video where we dive deep into the construction and chemistry of these rocket motors. For now, you can pause the video and have a good look at this diagram, which should give you enough information to be able to watch this video. Getting back on track, the second design choice that we made that we probably shouldn't have was the material for the nozzle and end cap. This time again, we thought metal was out of the question because attaching a metal nozzle to a PVC casing would evolve into some kind of complicated attachment mechanism that we do not want. We first tried using M-Seal epoxy composite, thinking that the burn time of the motor would be short enough that the M-Seal would not melt before the burn time is completed. It, of course, did not work. Following that, we tried using cement at different mixture ratios to see which one provides a good balance of strength and smoothness for the flow of gases. This kind of worked. We were getting good results sometimes, but sometimes the nozzle, or worse, the end cap, popped off because of the high pressure inside of the motor. This was despite the fact that we tried our best to maintain consistency between each batch of motors, making sure the cement mixture ratios and the environment were the same every time. At last, we added some epoxy into the mixture of cement and sand. This seemed to work magically and it provided very good cohesion and adhesion to the motor casing. To make these nozzles and end caps, we used a 3/4 inch PVC pipe and cast the nozzles and end caps into these pipes. When assembling the motor, these 3/4 inch PVC pipes would fit snugly after some sanding into the 1 inch PVC pipe of the motor casing, and then they would be bonded to the PVC casing using some epoxy resin. Overall, this was not a great design for a motor, maybe it wasn't even a good design, but it got the job done. In hindsight, if we had to make the choice between metal and PVC again, we would probably choose the metal. It's a lot less hassle, we know now because we did do that for our next rocket of Platoon, and generally a lot safer than PVC as well. Moving on, another subsystem that took a few tries to figure out was the recovery system. Now, I'm going to tell you something very important. Come closer. Do not make parachutes out of garbage bags. It's a stupid idea. Just don't do it. In an attempt to make the design simple, we chose to make the parachute out of everyday materials. This led to a garbage bag parachute, and it worked well during ground tests, but it tore on both occasions that it flew during flight. So we quickly switched to nylon instead. Apart from the parachute, a crucial component of the recovery system was the flight avionics and the ejection system. And I'm pretty sure these were sentient beings communicating with each other, coordinating failures so that one of them failed in one launch and the other one in the other. On a more serious note, there was nothing wrong with the designs of either. It mainly boiled down to manufacturing quality. We were a small team with small funds, and sometimes we just did not have those expensive and high quality manufacturing options on the table for our components. Our avionics system comprised of an ESP32 microcontroller to make the decision to eject the parachute, a BMP280 barometric pressure sensor to measure the height of the rocket, a battery to power this, and two transistors in parallel that switched on the current to the igniter that caused the opening of the ejection mechanism. The ejection mechanism is a simple spring-based piston that is held back by a cotton string. When the parachute is to be opened, the flight computer sends the signal to burn the igniter, which burns a bit of black powder, resulting in the cotton thread burning and releasing the spring. However, we used to make the PCB for our flight computer ourselves using the ferric chloride etching process, but this process did not produce the most reliable connections. This means that even though the processor sent the command to fire the igniter, sometimes the current just did not get to the igniter. And we all know what happens when parachutes don't open, don't we? Other times when the avionics worked fine, either the parachute got tangled or the ejection system could not push hard enough to open the rocket. All in all, not great production quality, but during the length of the project, we did manage to get some mostly successful launches out of the rocket. In the end, we decided to conclude the project at those mostly successful launches. This is because we understood the inherent problems with the design well, and fixing them would require a complete redesign, effort that we would rather spend in making a bigger and more advanced rocket without no constraints from scratch. Besides, the objective of this project was to be a stepping stone, a platform where we could learn about how to build model rockets. And I must say that it has served its purpose really well. This project has enabled us to dream of and achieve much bigger and much more ambitious goals, something that we will talk about a lot in future videos. So it was time to conclude the project on that note and start focusing on bigger rockets with bigger goals. Before ending this video, I would like to thank Tanmay sir and his initiative Tanmay's Amazing Space for sponsoring a part of this project. He has enabled so much in our team thanks to his financial and moral contributions. If you don't know, Tanmay's Amazing Space has been passionately teaching astronomy since 1986 to various age groups. They have also recently opened a space studio in Ahmedabad where you can visit and experience space for 2 hours straight in a way you have never before. If you're a parent or school teacher in Ahmedabad, the Tanmay's Amazing Space Studio is a must-do activity with children. Check the description for a link to their website or scan this QR code. I would also like to thank C4E.in and TeziApp.com for supporting our team financially and even more so morally. It is because of businesses and people like this ready to donate to student projects that a community of builders can thrive. We wouldn't have been able to do nearly as much as we have without the support of people and companies like this, and many more who chose to be anonymous. So that's it for this video. See you in the next video where we will talk about a bigger rocket with a crazier objective. See ya.